Hi everyone. Today I will going to explain you John Teller distortion. So the John Teller distortion was proposed in 1937. In 1937, John and Teller proposed a theorem to explain the d-Orbital splitting pattern of distorted octahedral complexes. Right, it actually explaining the d-Orbital splitting pattern of distorted octahedral. What is the distorted octahedral? We are going to see. Let us see the statement of the theory. Right. The nonlinear molecules like octahedral complexes with asymmetric degenerated electronic configuration is unstable and will undergo further distortion where degenerated states splits will the where the degenerated states will undergo for the splitting. Okay, we'll get degenerated states will get split right. This is what the statement. So actually what we have to know that initially here terminology, two three words are maybe unknown for you, right? Let us discuss first that, so that the statement actually come to know exactly what it means. Okay, so firstly, John Taylor's theorem is describing the d-Orbital splitting pattern of distorted octahedral, right? Actually the meaning of distorted is altering the structure, the alternate, it means, right? Distorted octahedral nothing but alternate octahedral structure, right? So here the octahedral may be slightly deviates. You know that what it means by octahedral. The octahedral is that where it has six coordinated complex. Octahedral complex means six coordinated complex, where along the x-axis two ligands, along the y-axis two ligands, along the z-axis 2 ligands, right? Here all the 6 ligands whatever in the octahedral complexes, right, having equal bonding, when they're having equal bonding, that particular octahedral structure will be called as regular octahedral, right? Most of the time this will takes place, right? Most of the time this will takes place where the metal to ligand bonds in all coordination directions, right, in all 6 ligands will be one and same, mostly one and same, right? That is what the regular octahedral. So distorted octahedral, altered octahedral, right? Distorted means altered octahedral, right? So such altered octahedral where what happens is the metal to ligand bonds will be vary from one to other, right? There will be two types of metal to ligand bond lengths will be takes place, right? That is what we will see in the distorted octahedral. Actually it has to have all 6 bonds should be same. When that is there, you will be say that regular octahedral. When there are some number of bonds are shorter, some are lengther, right? In that manner, when it is there in 6 bonds, right, some are shorter, some are lengthened bonds, when it takes place, that would be called as distorted octahedral. Okay, that is what about the distorted octahedral complexes, which it means. So the statement, when it comes, the statement saying that the non-linear molecules, right, non-linear molecule, it means you know that structure when there is a linear, right, in a single when we take the pen, right, a line, when it is defining the structure of some molecule, it will be said as linear molecule, right? Rather than a line is defining the structure, it will be called as non-linear, right? Such as octahedral, right? Octahedral cannot be defined with one single line, right? It has all three-dimensional shape. Okay, so such three-dimensional shapes are called as nonlinear structures, right? The nonlinear molecules like octahedral complexes, right, when they have in the octahedral complexes, when it has the metal having asymmetric degenerated electronic configuration. Here you have to know that what it means by asymmetric. Before asymmetric meaning, you have to know the exactly meaning of symmetry. When we know the symmetry meaning, you can alter, you can reverse the symmetry meaning for asymmetric, right? Isn't it? So far we have to know symmetry. Symmetry is that, right, in fundamentally, in generally, when we discuss the symmetry, right, it means that distribution, right, distribution, if we consider a molecule, right, distribution of uh, atoms in all direction is equal, right, that would be symmetrical, right? uh, Distribution of something in a in a in a in a material, when distribution is equal in all direction, that would be called as symmetrical, right? So if we take this particular pen, right, it has two directions, left and right, right and left, right? In these two directions, is that having equal distribution? No, it may not be exact, right? When it come to peak of right, right, exact right, right, it has an sharper side. When it come to left side, it has uh, round, right, bold or thick side, right? Sharper side, thick side, right? Right side thick side, left side sorry, right side sharper side is there, left side thick side is there. So it may not be called as symmetrical, right? The distribution for left to right, it is not same, right? When you choose the chalk piece, right, when you choose the chalk piece, it is cylindrical, right? From left to right, right, most of the chalk, most of it, it would be equal. Otherwise you can take fan, ceiling fan, right? Ceiling fan having three wings, most of the time it has three wings, right? The three wings of ceiling fan, when we observe, right, it has all balance, right? All balance in an 3 wings, right? In 3 sides the wings are one and same, right? Uniform, they have size, right? So such a a thing or a material having same distribution in all direction, then it will be called as symmetrical. Okay, right? So when it come to asymmetric, nothing but reverse of symmetrical. Unequal distribution of in all direction, in different directions, right? Unequal distribution of in different direction will be called as asymmetrical, right? So asymmetrical electronic configuration in degenerated states, right? In degenerated state, electronic configuration should be asymmetric, right? So if you go for particular about the degenerated electronic configuration of octahedral, after getting splitting pattern in octahedral, we are getting two degenerated states, that is what T2G and EG, right? So you consider T2G, right? T2G having three orbitals, right? Isn't it? Triply degenerated state is denoted with Mulliken symbol of T2G, isn't it? In octahedral complexes, right? So where three orbitals are there, dxy, dyz, dzx, which are in an equal energy. So far you are forming an group as it is T2G. Okay, so in this T2G triply degenerated orbital state, when electrons are unequally distributed, right? When electrons are unequally distributed, such as T2G1, if it is T2G1, where the one electron can be either it comes into dxy or dyz or dzx, any of one, the other left two will be empty, right? That will be unequal distribution or not, isn't it? Right, that is what unequal distribution. If it is T2G2, right, two electrons can be distributed in two of the dxy, dyz, dzx, the other one will be empty, right? The other one will be become empty. So that case also, T2G2 case also, unequal electronic distribution in T2G. T2G3 when it come, T2G3 when it come, it has all three electrons in all three orbitals. The dxy will have one electron, dyz will have one electron, dzx will have another electron, right? So when three T2G triple degenerate state having three equal electrons, right, it would be called as equal electronic distribution or symmetrical electronic distribution. When it comes to T2G1 or T2G2, it would leads to unequal or asymmetric electronic configuration, right? So where here, when it come to particular of this particular theory, the unequal electronic distribution has to be there, right? So that when it takes place, the octahedral complexes with such unequal electronic distribution, right, what happening, thus unequal electron distribution is unstable. He is stating that it would be unstable, right, in distorted octahedral complexes, right? The unequal asymmetrical electronic configuration, it will be unstable. Thus unstable electronic configuration will undergo further distortion, which means it will undergo in further splitting, right? It will go further splitting, right? That is what the theory, right? Here again, for undergo distortion in nothing but altering the splitting pattern, right? Actually octahedral splitting pattern is T2G and EG. T2G in lower energy state, EG in higher energy state. But distorted octahedral having asymmetric electronic configuration will be unstable, which means that T2G EG states are unstable, that undergo distortion. It nothing but the further splitting will be takes place, the altering the T2G EG states will be takes place, where the splitting will be takes place, right? The T2G never be T2G in the distorted octahedral where asymmetric electronic configuration. The EG will be never be EG in the, right, distorted octahedral where asymmetric electronic configuration when it has, right? That is what the exact statement of John Taylor distortion, right? Is you got? So octahedral, distorted octahedral complexes having asymmetric electronic configuration, right, will undergo further distortion, further splitting, right? That is what the John Taylor theory, right? So let we go with one example. With one example, when we explain the exact theory and exact splitting pattern, when we get exactly right. So here we will take the copper complex, copper to complex, copper to octahedral complex, right. Here non-linear octahedral complex with copper 2 ion has D9, which means T2G6 Eg3, isn't it? Copper to octahedral complex, nothing but non-linear complex. As we consider octahedral, it is non-linear, isn't it? Right. So non-linear octahedral complex with copper 2, where it has D9. When it is undergoing splitting of general splitting pattern of octahedral, it will have T2G6 Eg3, right. This is the case, has T2G Eg T2G6 Eg3, right. T2G6 Eg3, T2G6 Eg3, nothing but T2G6 Eg, nothing but T2G6 Eg, nothing but T2G6 configuration will be symmetrical, right. Symmetrical, all three orbitals of T2G having 2 electrons in each, right, where it would be said as symmetrical. But when it come to Eg, Eg have two orbitals, d x square minus y square, d z square, where it having 3 electrons, nothing but one of the orbitals, either it will be T2G, either it will be dx square minus y square have 2 electrons, dz square have 1 electron, or it would have dx square minus y square will have 1 electron, dz square will have 2 electrons. So which will be called as asymmetric, has d9 asymmetric electronic configuration, right, isn't it? The statement is correct with respect to this. What we take an example is effect will be correct for the statement, right. The statement of John Taylor distortion is saying that non-linear complex it should to be, right, where it has to be have asymmetric degenerated electronic configuration like this, right. Octahedral complex we taken, which is non-linear and having asymmetric electronic configuration of Eg3, right. So here what is happening, how the splitting pattern is taking place is explained by the John Taylor, right. So what we are expecting, these T2G Eg states are never be stable, right, as per John Taylor distortion, right. This particular T2G Eg degenerated states will be unstable, they undergo further splitting. Why they are going splitting, right, how they are going to splitting, we will say. And the distorted octahedral, what we are stated initially, right, distorted octahedral, the metal to ligand bonds are unequal, right, 6 metal to ligand bonds are, right, will be unequal, right. Some will be shorter, some will be lengthened. What type of unequal bonds, how it can be taking place unequal bonds, we will see here, right. So here when it come to the asymmetric electronic configuration of Eg, right, it has two cases. The Eg3 may have dx square minus y square 2 electrons, dz square will have 1, right. This is the one case, case A. Or it can also have the second case, Eg3 can be have dx square minus y square in 1 electron, dz square will have 2 electrons, right. In first statement, right, in first case, right, what happening, the dx square minus y square will have 2 electrons, dz square will have 1 electron, right? In this particular case, right, case A, Eg 3 electrons, dz square, sorry, dx square minus y square will have 2 electrons, dz square will have 1 electron, right? What happened here is, in this case, the complex, the octahedral complex, right, having dx square minus y square having 2 electrons, right, where the dx square minus y square having lobes along the coordination axis. Along the x-axis, left right will be two lobes, and front and back in z-axis, in y-axis there will be two lobes, right? So having 2 electrons, higher electron density compared to z square, right? So which means dx square minus y square having 2 electrons, nothing but along the x-axis, along the y-axis, right, the electron density is more, right, rather than z orientation. When it comes to dz square, it means what? The lobes are up and down. The lobes are up and down. In that up and down direction, only one electron is there. In the left, right, and front and back, right, as it is d x square minus y square, left and right x-axis, front and back y-axis will have two electrons, larger electron density, right? In thus left and right, front and back, x direction, y direction having larger electron density, right? Where when there is a large electron density in x direction, y direction, the ligands, right, in octahedral we know that the ligands are approaching axially, right? Along the x-axis, two ligands will be there. Along the y-axis, two ligands will be there, right? Such as lastly we explained, right? This is what octahedral, right? Along the x-axis, two ligands. Along the y-axis, two ligands. Along the z-axis, two ligands, right? Right. So while it having dx square minus y square 2 electrons, higher electron density, on x direction, y direction, the electron density is more. So when there is electron density is more along the x-axis and y-axis, right, the repulsive interactions between ligand to metal electron density will be more and more, right? So what happens? The metal to ligand bond will become slightly larger. It will be get lengthened, right? It will get lengthened, right, due to the higher electron density along the x-axis and y-axis. So the structure will be like this, becomes like this. Along the x-axis, along the y-axis, metal to ligand bonds will be slightly get lengthened, right, will get lengthened. Whereas in z orientation, having only one electron density, lesser electron density, the metal to ligand bonds are slightly shorter, slightly shorter. Like this it happens, right? Right. So far, right, when this is happening, right, in this particular case, right, T2G, sorry, Eg3 dx square minus y square having 2 electron, dz square having 1 electron, the octahedral structure alters to right, x y axial bonds, axial bonds, axial bonds get lengthened. Than z axial bonds, z axial, right, z axial bonds, metal to ligand bonds, right, z axial metal to ligand bonds, metal to ligand bonds, right, right. This particular, which is called as distorted octahedral. This distorted, right? Is it distorted or not? In octahedral, the metal to ligand bonds all should to be one to other, 6 bonds should to be one to other same, right? But here what happening, 4 bonds are lengthened, 2 bonds are shorter, right? So this could be called as distorted octahedral. This distorted octahedral complex called as Z in structure, Z in octahedral or Z in structure, right? Z in structure. So this Z in structure, when we consider, right, we have to give splitting pattern. Z in structure, splitting pattern when we draw, right? Once again I am drawing the structure, Z in structure, where X bonds, X axial bonds, Y axial bonds are lengthened, and Z oriented ligand bonds are shorter, right? Right. This is Y axis, this is X axis, this is Z axis, right? To give the splitting pattern, you know that, right? How to give, right? The EG orbitals, dx square minus y square dz square, right? Which are the orbital getting more interaction with ligand sites, that will have more repulsive interactions, and that will undergo high unstabilization, right? Get destabilizes more effectively, and that will reaches to higher energy. Which orbitals are getting lower interaction, right? Getting lesser interaction with ligand sites, that will get stabilizes and reaches to lower energy, isn't it? That is what the splitting pattern, right? The fundamental thing to be get splitting, right? So here when we observe, right, when we observe the metal to ligand bonds in X orientation, in Y orientation, the metal to ligand bonding is very lengthened, right? Strength is very less, right? As they are lengthened bond in X direction, Y direction, right, the interaction between metal orbitals to ligand, right, will be very lesser effective, will get very lesser effectively the interaction it takes place, right? As they are length and bond, when they are go far away, right, what happens, the interactions will be very less, right? So you know that if we think that two opposite persons are there, when they are going to be quarrel, they has to come very closer, so that the quarreling will be in higher extension, right? When the two opposite persons, when they are going far away one to other, they are going far away, is that quarreling it takes place? No, no, right? Same thing here, right? The metal to ligand, right, the gap it is taken place, as the metal to ligand bond length is becoming more lengthened, right? The interaction between metal orbital to ligand negative charge will be getting lesser, right? So what happens, it get, it never have any repulsive interaction. When there is no repulsive interaction between metal dx square minus y square orbital, right? We are discussing dx square minus y square orbital, which is oriented in x direction and y direction. In x direction, y direction, the dx square minus y square orbital will take place. Thus particular orbital, as the ligands in this particular orientation is very lengthened, right, having lengthened bond, the interaction between dx square minus y square and ligands will be very less. So far this particular orbital get stabilizes and reaches to lower energy, lower energy. Where when it comes to dz square orbital having lobes along the z axis, right? Along the z axis, the metal to ligand bond is what? Very shorter, right? Shorter metal to ligand bond, nothing but the interaction of ligand to metal will be very effective. Ligand to that particular oriented dz square orbital interaction will be very high. So having high interaction between dz square orbital and ligand negative charge, right? It get destabilizes, repulses, get destabilizes, higher energy reaches to higher energy, right? So this is the case of eg3, where dx square minus y square will have 2 electrons, dz square will have 1 electron, right? So far the splitting will be like this, right? The eg state never be stable at the eg level. It will become further splitting, it undergoing further splitting. There is non-degenerated or singly degenerated states will arises. One is lower in energy, other is in higher energy, right? This is the first case, right? Where Z in structure, it is Z in octahedral complexities, distorted octahedral complexities. Okay, so in second case, right, Eg3 has dx square minus y square in 1 electron, dz square will have in 2 electrons. In this particular case, what happens is in Z oriented there will be 2 electrons, large electron density. In XY oriented, right, in Z orbital 2 electrons are there, nothing but on Z orientation electron density is more in metal ion, isn't it? In dz square orbital 2 electrons, large electron density when it is there, nothing but in Z axial orientation the electron density, metal electron density is high, right? That is what, when the metal electron density in high in Z orientation, right? So what happens, the repulsive interaction will be takes place between that particular Z oriented ligands to thus dz square orbital, right? So far here the distortion it takes place as that the Z metal to ligand bonds will be get lengthened, right? Whereas in dx square minus y square having only one electron, which nothing but in x axial orientation, in y axial orientation electron density is less. So when there is electron density is less in the x orientation, in y orientation, thus oriented ligand sides, right, will have negative interaction is very less. So far they comes closer to have bonding with metal. So far the metal to ligand bond will be very shorter, very shorter, right? Like this it happens, right? In x orientation, in y orientation, as the orbital of dx square minus y square having one lesser electron density, metal to ligand bonds are very shorter. When dz square having higher electron density of 2, the interactions is more, so the metal to ligand bonding will be weaker and lengthen, right? So this is Z oriented ligand sites and lengthen bond it takes place, right? So here with this, in this case, in this Eg3 dx square minus y square 1 electron, dz square 2 electrons, the Z axial metal to ligand bonds will get lengthen, and x comma z axial metal to ligand bonds shorter. Right. This distorted octahedral complex will called as, how it could be called as Z oriented ligands are lengthened, it will be called as Z out octahedral, Z out octahedral complex. Right, this will be Z out octahedral. Right, so here in this case, right, the splitting pattern, how it could be, initially dx square minus y square dz square, right, having one electron in dx square minus y square, two electrons in dz square. Right, as along the Z orientation, metal to ligand bonds are very lengthened. Right, the metal to ligand weaker bond it is taking place. When weaker bond and lengthened bond it is taking place, the interaction of negative interaction of this particular ligand, Z oriented ligands with metal valency d Z square orbital will be very less. Right, having far away, going far away from negative charge of ligand and negative charge of the dx square minus y square electrons, the quarreling will be very less. Right, the interaction will be very less, there will be no interaction taking place. Right, with respect to dx square minus y square dz square orbitals and ligands oriented in z axial orbitals. Right, z axial ligands. Right, so far thus particular dz square orbital gets lower its energy, where the other dx square minus y square will get excited. Since what? Because of the metal to ligand bonds in x orientation, in y orientation, metal to ligand bonds are very shorter. The interaction of ligand negative charge with metal valence electrons will be effectively it is taking place. Right, even though it having single electron, the interactions will be effectively it is taking place as there are shorter bond lengths between metal to ligand. So effective interaction between the x square minus y square electron with ligand negative charge, thus it is effectively get excited and reaches to higher energy, will reaches to higher energy. Right, this is what the splitting pattern it takes place in Z out structure. So you may tell that, you may ask that, right, in these two structures, right, in distorted octahedral, this is distorted and this is also distorted octahedral. So what could be in practically existing distorted octahedral structure? It is the Z out structure is very practically existing structure, distorted octahedral structure. Why this has to happen? Why not the Z in structure, Z in octahedral structure is existing? Because in Z in octahedral structures, when we see the strengths and weak bonds, right, strengthened bonds and weakened bonds, number of strengthened bond, number of weakened bonds, when we say here 4 are weaker bonds, metal to ligand bonds here 4 in x orientation, in y orientation the metal to ligand bonds are lengthened, which means they are the weaker bonds, isn't it? Right, so all 4 in x orientation, y orientation weaker bonds it is taking place. In 2 z orientation metal to ligand bonds are strengthened bond, 2 only the stronger bond, 4 are the weaker bond. Right, when it come to Z out structure, right, then Z out structure, metal to ligand bonds in x orientation, in y orientation shorter bonds it is taking place. Right, as the x orientation in y orientation shorter bonds, the bonding strength will be higher. Right, so here in direction of x and y, right, stronger bonds are taking place and there are 4 stronger bonds, only 2 bonds along the z axis lengthen and weaker bond, this particular structure, Z out structure, will have only 2 weaker bonds, 4 stronger bonds, right? Having 4 stronger bond, only 2 weaker bond, this could be a very possible structure than this, since it is having 4 weaker bond, right? Naturally, it happens that which is more stronger, that could be exist more effectively, right? So in these two cases, this would be a more stronger bond, existing more number of stronger bond. This would be a stable structure than rather than Z in structure. Z out structure having 4 stronger bonds, only 2 weaker bonds. So far it exists, rather than Z in structure having 4 weaker bonds, 2 stronger bonds, right? So far this particular structure, Z out structure, is very possible structure in distorted octahedral. Okay, so altogether, right, we have to describe all the d-orbital splitting pattern in distorted octahedral, right? Such Z out structures, right? When we see that, the 5 non-degenerated orbital, right, if it is regular octahedral, what happens? You know what happens? It has 2 energy states. In splitting, it generates 2 energy states. One is Eg, the lower energy is T2G. This is free metal ion. This is octahedral, regular octahedral. Where this regular octahedral, when it is distorted octahedral, the Eg state and T2G states never be stable. They undergo in further splitting. When they go under in further splitting, the dz square will be lower energy, dx square minus y square in higher energy, same together, dxy in higher energy, dyz and dzx in lower energy. This is how the T2G, when it get in splitting in distorted octahedral, it has lower energy states of 2 orbitals, higher energy state of 1 orbital. Same that Eg, when it gets splits, lower energy state of dz square and higher energy state of dx square minus y square it taking place, right? After all these getting splitting, it would be indicated with Mulliken symbols, right? All these newly generated energy states will be symboled with Mulliken symbols, right? This singly degenerated orbital can be symboled with B1G, right? This will be indicated with A1G. This indicated with B2G. This doubly degenerate energy state will be indicated with EG Mulliken symbol, right? So this is how the d orbital having splitting in distorted octahedral. This particular splitting pattern for distorted octahedral complexes. Right, Z out distorted octahedral complexes, right? So this is when it is taking place. Distorted asymmetrical electronic configurated complexes will have such splitting pattern. Asymmetric electronic configuration, when it arises when there is an T2G 1, T2G 2, T2G 4 or T2G 5. In these electronic configurated T2G energy state, when it exists, it would be distorted. In EG level 1, 3 electronic configurations, right? T2G1, sorry, EG1 or EG3 are the distorted states, right? Distorted asymmetric electronic configuration. These are the asymmetric electronic configurations, isn't it? Right. When T2G having single electron, nothing but the other two will, one will be filled with one electron, two will be empty. So it would not be called as equal distribution of electron in T2G. Either in, even if we go for T2G2 also, two orbitals will be filled, two electrons, the other will be one empty. That is also asymmetric electronic configuration, asymmetric electronic distribution. When T2G4 also, one orbital will have fully filled two electrons, the other will have only half filled single electron. That is also unequal distribution. In T2G5 state also, right, two orbitals will get fully filled two electrons, the other one, third orbital will have half filled single electron. That is also asymmetric electronic configuration, electron distribution, right? Even in the EG state, one electron or three electron will be asymmetric electronic configuration only. So when we go with examples of metal ion, right, manganese with +3, manganese +3 will have T2G4 electronic configuration, isn't it? And what we can say, cobalt +2, T2G6 EG1, right, copper +2, T2G6 EG3, like that. These metal complexes, like this, many more complexes are there. Such metal complexes has asymmetric electronic configuration. When such asymmetric electronic configured octahedral complexes will exist, distorted octahedral structure. Thus distorted octahedral asymmetric electronic configured metal complexes will have such splitting pattern, where higher energy state of B1G, next level will be A1G, next will be B2G, next will be lowest energy state of EG, right? This is how the distorted octahedral splitting pattern taking place, right? So I think you might got uh, exactly what about the John Taylor distortion theorem, and within one example I given all the explanation why it has the distorted structures and why it having the splitting pattern and how it is getting the splitting pattern. Exactly, I have given the explanation, right? If you have any doubts, right, you can give your doubts in comment section, right? I will upload this on YouTube, right, in my channel. So you can give your uh, any doubts or any compliments on the uh, comment section, right? So here I stop. By next we'll continue next topic. Okay, thank you.